Problem set 9 is mostly going to deal with lessons 5A and 5B. So it's going to involve some gas manipulations and also some ideal solutions. So in problem 1, we're given a mixture containing acetone and chloroform, and we want to use a bunch of information to find out the number of moles of each of these that appear in the mixture. Now, we're given the partial molar volumes for acetone and chloroform. I'm going to use A for acetone and C for chloroform, and the partial molar volumes are given here. I want to emphasize that these are the partial molar volumes for this mixture. That is to say, they would change if we had different proportions of acetone and chloroform in the mixture. Now, what we're asked for in part A is the number of moles of each. So in other words, the number of moles of acetone and the number of moles of chloroform. So these are the things that we want. There are two unknowns. We're given that there is a total mass in the mixture of 454 grams. So we have a total mass, and we have partial molar volumes. And what else do we have? We have the mole fraction of chloroform. So XC is 0.4297. So how can we get after this? Well, I'll just mention that we have two unknowns, and you might find that there is just one equation that you can really relate these things to in order to determine the total mass, for example, of this mixture. Well, once you have a mole fraction, you now have a connection between the two components. And that connection should allow you to find both of these. Now, I'll offer as a hint that it might be worthwhile to take a look at the total moles of gas, that is to say, the combined moles of acetone and chloroform, and see if you can't express these two quantities in terms of this quantity. And if you can, then you might be able to generate one equation and one unknown, which you can then solve to get the answer to the problem. All right, in part B, you have a volume of unmixed components. So these are the pure molar volumes for acetone and chloroform, that is to say, as individual quantities. So you'll need to use these along with the mole fractions, with the total moles that you're given, to determine some kind of volume for the acetone and some sort of volume for the chloroform. And then you're going to want to combine these and compare them with the volume that you have up here, your total volume for the thing. And that way you'll be able to tell if the effect of mixing these two was to cause the volume to expand or contract upon the mixing. All right, it's an interesting problem, and I hope that you can work through it because I think it illustrates the partial molar volume concept very well. All right, in problem 2, we now have a pair of gases that are in a binary solution with one another. Or actually, it's not gases, they're liquids that are in a binary solution with one another. And they have their vapor pressures are given by these expressions. And these might look familiar. This is very much like one of the basic skills problems that you were given to work on in lesson B. Now, when we have a situation like this, and we have basically an ideal solution, means we can use Raoult's law for some of these. And in particular, really all we need to do in calculating the, what is it we're asked for here, for the total vapor pressure of this mixture, really all we need to do is use the formulas and plug in the numbers that we have. So I would say that this part of the problem is very straightforward. And I say that meaningfully. It won't require, it's not tricky, it's not requiring much devious thought to get to the answer. All right, in part B, we're now going to assume that this vapor is an ideal gas. So what can we assume from that? Well, I'll give you another hint. Dalton's law of partial pressures should be applicable if it's an ideal gas. So use that, and then you might be able to get the mole fractions of each component in the vapor phase. Okay, moving along to problem number 3. This is an interesting problem because we're now moving in the direction of temperature composition diagrams. And we're given expressions that tell us not what the actual vapor pressure is, but what the vapor pressure of the pure substance would be at different temperatures. Okay, so really what we have here are equations that tell us what P sub A is as a function of T and P sub B is as a function of T as pure substances. Now, we're going to assume that this is an ideal solution, all right? So think about what that means in terms of vapor pressures. And what we're going to want to find is the mole fraction of the the carbon tetrachloride. So we want to find this mole fraction in both the liquid and the vapor phases. So the standard notation we use is X to indicate the mole fraction in the liquid phase and Y to indicate the mole fraction in the vapor phase. Now, there is a key piece of information that you're given in this problem. You're given an ambient pressure of 1.04. Now, why is this important? Well, one of the pure partial pressure, one of the pure pressures that you're going to be given is greater than this ambient ambient pressure, and the other one is less than. So in other words, these two things are going to bracket this value for pressure. So that's going to give you a key to getting into finding the mole fractions of these things in the liquid phase. We're going to be assuming an ideal solution, so that means probably Raoult's law is going to be applicable here. So you can use that and the relationship between the two mole fractions in the solution phase, along with their pure substance vapor pressures and the total pressure. You should be able to find the mole fractions of each component in this solution phase. Once you have that, all right, then you should be able to use Dalton's law, for example, to get the mole fraction of these things in the vapor phase. So this is, I think, a really interesting problem in that you're given some key pieces of information, things that you presumably could measure experimentally for a pair of substances that are in a narrow temperature range, and be able to get the mole fractions in both the solution and the vapor phase out of this. All right, now if we suppose that it's heated up slightly to 358, now this isn't heating up a lot. We're at 352 in the first part and 358 in the second part. All right, but we're going to say the solution has the same composition. All right, so if it has the same composition, we can use the results for these factors up here from part A. So we can use our mole fractions XA and XB for part B, and then determine what the total vapor pressure is. But we'll have to update the two vapor pressures of the pure substances because we're at a new temperature. All right, now because we've only increased the temperature by 6 Kelvin, don't expect a major change in the result. There will be a small change in the result, but if you get something that's wildly different from the answer that you got in the first part, you're probably on the wrong track. All right, good luck with that one. All right, in the last problem, we're now given a mixture of benzene and toluene, and this is one of the classic examples of an ideal solution. So once again, we're in an ideal solution, and we're between these temperatures. Now, I'll note parenthetically that when we're told that we're going to be creating a temperature composition diagram, that is only valid between the boiling points of the two species. So, for example, if you have a diagram that looks like this, where this is the mole fraction of one of those components, and its boiling point is up here. This is temperature on the vertical scale. And this is its boiling point when it's pure, and this is the boiling point of component B, then you're going to have a diagram that's going to look something like this, right? But you're only going to be able to span temperatures that are between the boiling point of B and the boiling point of A, all right? So that tells you that these probably are those. You might be able to use this equation, this pair of equations, to determine which one of these might be closer to 353 and which one might be closer to 385, but you need to think about what's involved in making that determination. All right, so these problems here are actually pretty similar to problem 3. Okay, not too different from problem number 3. You'll get to do this at 2 different temperatures, so I've highlighted them to make sure you realize that these are different temperatures. So you should be getting different mole fractions for these. And I do want you to include your copy of the temperature composition diagram. It may or may not look like this. All right, but you need to submit a copy of that with your problem set when you submit your work on this particular problem set. All right, these should be good problems to work. They should illustrate the concepts that you've been working on in this pair of lessons. And if you have any questions, please do not hesitate to contact me.